Alright, so for this part, the thing I was rambling about when I was flying was me talking about an equation that would solve for what height you need to be before crossing a terrain where you have no outs, like the water. How high do I have to be if I want to cross the river to get to beach side from mainland side? I went to Google Earth and used a little measuring tool. In general, it's about 2.5 miles from anywhere usable inland to someplace that's usable on the beach side. So I wrote stuff down. I want to share that with you. So I'm just going to be a nerd and bear with me. So, okay. First, let's get some concepts out of the way. So you have, wow, I don't know what that's about. Let's edit that out. Ooh, I want the pen tool. Yeah, cool, okay. All right. So first, let's get a concept kind of out of the way here, so we're all talking the same language, right? You got your little dude. Let's see, we'll zoom in for a little dude here. Dude man. Got your dude. This is you. There you go. You're happy. You're so happy. Alright. So there's you, right? You're gonna fly this way. So, if you're going that way, then let's just say you have compass rose around you, right? North, east, south, west, 0 degrees, 90 degrees, 180, and 270. And this is 359 over here, right? Okay. So this concept is you have wind coming from a direction, let's say this direction. If you look at that, we can say that it creates an angle, right? Right? So you're going this way, wind is going this way, and this angle theta. This one looks pretty small, so let's say it's like 15 degrees. All right? So there's the concept. That's important for later. All right, so there's that. What else I got? Okay, yeah, high school geometry. Cool story, cool story. All right, so you have a right angle triangle, right? You got one of these. You have your hypotenuse. You have your, we're solving for this angle. Your adjacent side and your opposite side, right? So we're gonna use cosine because SOHCAHTOA, right? So we're gonna use this one because it has the adjacent and hypotenuse. So the length of this piece here, which is the vector we want that I was talking about. That is the magnitude of the hypotenuse times cosine of theta. All right, so there's some geometry refresher for you guys. Hi Leaf, how you doing? So okay, there's a refresher. As a side note, I haven't reviewed my video with the audio marks that I made. Wow, okay. Where I said, oh, this is my altitude at this time and that kind of thing. But I did look at my Suunto watch data. Seriously. And I wrote down some notes from it. So from the Suunto timeline at 19 minutes and 19 seconds, right? I was at about 53.12 12 feet. At 32.21, I was at 702 feet. So this was when I went to idle, and then before throttling out. All right, so this is a descent of 4610 over 13 minutes 2 seconds, or 782 seconds. And if you look at that, that goes from 5.895 feet per second all the way down to 4.02 miles per hour, which is something we can use, right? So I just converted them. Descent, idle. And my propeller, wow, you really did something with my camera there. All right, so my propeller has a clutch so it doesn't spin when I'm idling. That's neat. How do I make that go away? All right. So, also, okay. Oh God, why? Okay. So, Sunto vertical speed indicated, you know, it has a graph. It indicated between, it went up and down quite a bit, so I just wrote down stuff. 347.5 feet per minute to, well, 395 feet per minute. I wrote down an average, right? Oh, no, I totally did that wrong. All right, hold on, 1 second. I wrote down the wrong thing. Sorry. 305.1 feet per minute to 390. I can't even read my own writing. I think that's 390 feet per minute. That averages to 347.5 feet per minute, or 3.95 miles per hour. So, based on the two methods that I use to figure out what my vertical descent rate is, they're consistent. So we're just going to say 4 miles per hour descent. Okay? Okay, cool. So let's think about something else, right? So you got your little dude. He's up there with his butt fan, and you know, he's looking super happy, right? He's got his wing with a cool airfoil shape. All right, cool, cool, cool. Lots of lines. Looks like a spider web of lines. All right, cool. So he's up there, right? His flight path goes like that, right? He's descending. So you think of that also as a triangle. So like I said before, my wing typically will go 24 miles per hour all the time, all day long. It's super happy, right? So if you're going 24 miles an hour and you have that 9:1 glide ratio that I talked about, the hypothetical 9:1 glide ratio, then if that were true, then this would be X miles per hour too. And you can go from miles per hour to miles like directly here. So it would be 24 divided by 9. Oh my God. But it's not. Instead, it's, let's see, glide ratio is 24 miles per hour. Excuse me. Divided by 4 miles per hour equals 6.2 not 9 to 1. So mine was doing 6 to 1, not 9 to 1. And maybe that's because I'm heavily loaded on my wing, because I'm a fat boy. But I don't care. The thing's beautiful. I know what my number is. It's 6 to 1, like pretty much on the nose. 6 to 1 glide ratio. All right. So now that we know that, and we're going to say also that, yeah, let's get some color in here. So we have this one, have a 6 to 1 glide ratio. What else we got? Those are the things we've solved so far. Cool. All right. So, with our data, I went off to figure out my mythical equation that I've been thinking about, right? So, let's do that. Let's see. I want a new one of these. All right. Okay. So I'm going to give a bunch of variables, right? I said there's variables. So we have our vertical speed, which is 4 miles per hour, as we just found out, because we did the math, how much I descended over time. So I descended at 4 miles an hour on average. Airspeed, that's how fast I'm normally going in no wind condition, according to my watch, which tracks me ground speed, which if there's no wind, that equates to airspeed, right? So happy wing is 24 miles per hour. All right, so that I called it wind speed onset. Now, that goes back to this concept. So you have wind, right? It's coming at you at an angle, okay? So wind speed onset is, like we discussed here, it's going to be the magnitude multiplied by cosine and the angle that it's incident to you. So, like I said, if you're here, you're flying this way, the wind is coming at you this way, this angle is theta. That angle is what we put here. Here. Okay. So, now that we know those things, pretty sure I wrote wind on here somewhere. All right. Wind speed onset is, according to your research, whatever the prevalent wind is that day, we're just going to call that wind speed. And magnitude bar on it. Wind speed times cosine theta, which is, like we just discussed, the angle offset from where you are. And that can be from 0 to 360. You plug that stuff in, if you've got a tailwind directly behind you, cosine 180 is -1. So that'll work out just great too. Or 359 to the right or left, it doesn't matter. You plug in any number with reference to the position you're pointing, it's gonna work. All right, and then speed over ground equals airspeed minus wind speed onset, right? How did I do that? Wind speed onset, wind speed onset. Right, you agree? So if you're flying, let's say 24 miles an hour airspeed, like you're supposed to, like my wing does, but you're flying into a 24 mile an hour headwind, you're paraparked, right? So your airspeed, which is a 24, happy wing, minus your wind speed onset, 24 mile an hour headwind, that's 24 minus 24 equals 0. So your speed over ground is you are parked. So that's what that is. Now, the important part, glide ratio equals your vertical speed divided by speed over ground. All right? Cool. So, glide ratio, vertical speed divided by speed over ground. All right. So, let's do an example. First, I'll give you the output of my function is how high do you have to be, right, to make that distance, whatever that is. So, required height is equal to your flight distance. In my case, it's 2.5 miles. That's my target distance. Geez, come on. Flight distance times glide ratio plus buffer. So this concept of buffer is how high do you want to be when you reach your target, right? So I want to go over to the beach, to the island. How high do I want to be above it and arrive there, right? So I need, like, let's say 400 feet to be above. So when I get there, I can look on the ground, check the local conditions, pick a nice spot to land and, like, commit, right? So buffer, that's what a buffer is. So required height, quote, is equal to flight distance times the vertical speed divided by airspeed minus wind speed times cosine theta plus buffer. Cool. All right. So, example. All right. So, flight distance for me was 2.5 miles, right? So I just looked on my, what's the name of the app that I always use? Come on, Ventusky, right? Ventusky. I looked on my Ventusky app earlier today just to see, like, what the wind was doing between Sebastian and the beachside, and so I wrote that down with respect to the direction that I'd be flying. So wind speed was 11 miles an hour at 40 degrees. Headwind from the right. And I just estimated, like, I kind of lined up on my phone the direction that I knew I'd be flying. It was quickly from mainland to the beach, and held up a pencil, and the little lines that come in to show you the direction of the wind coming in, it looked like it was about, 40 degrees off from that. So that's what I wrote down. And buffer is 400 feet, like I said. All right, cool. So, required height is equal to 2.5 miles equals 13,200 feet, by the way. It's 13,200 feet times 4 miles per hour over 24 minus 11 times cosine of 40 degrees. And then I put the miles per hour here because 11 miles per hour and 24 are both miles per hour, so I brought it out, which means you can cross it out also. Plus the buffer, which is 400 feet. And all you're left with are feet, right? So it's 3790. So I need to be 3,790 feet. Cool, right? Well, watch this. Example 2. Same data with tailwind. So, what did I call it? Yeah, wind speed. Wind speed equals 11 miles per hour at 120 degrees, which is tail from right equals 2190. So if you have a tailwind, obviously you don't need to be as high because it's going to push you there faster. So yeah, I think my equation's good. I think it's solid. So if you ever wanted to know how high do you have to be to fly to, over an obstacle, given that you have an engine out and you're just gliding, this is how you'd figure that out. I obviously recommend you figure this crap out before you go fly. Like, do your homework. So if I want to go to the beach for the first time, then I'm going to figure out what the wind is looking like before I go, and I'm going to make sure, like today, that I'd be 3790 feet at least before even getting over the water, at least. And that's just that's like if your engine went out right when you were crossing the water, you'd still be able to make it theoretically. But in reality, if your engine went out and you were flying into a headwind and you just crossed the water, you'd turn around and go back, right? But I think this method kind of guarantees that you're going to be safe no matter what you do. Because even if you wanted to just glide engine out like over the river, which is 2.5 miles across, you're still going to be fine. Except, important point, if we're flying, let me move this, you're flying this way, the wind is coming at you from this direction, you're going to be pulling right brake, right? Right brake to or left, I don't know. You're going to be pulling brake, right? Which is going to add drag. So I think that would definitely affect your glide ratio. And I'm pretty sure I was flying with brake the entire time, trying to not get spun around by the wind when I was coming down from a mile. So my glide ratio might be better than 6:1, but I know it is at least 6:1, so that's just going to be my number now. With how my trims were set up and stuff, which I think they were neutral when I flew, I think. But yeah, that was kind of fun. Long-winded, but it was super fun. So there you go. Math for the win. Thank you. Bye. Oh, before we say bye, subscribe, hit the little bell icon, leave comments. Thank you. Bye.